Hi everyone, Mr. Ang here. So here is the video for chapter 6 on energy. So for this first part of the video, we are going to go through what energy stores and transfers are, and here are the learning outcomes. One, to understand that there are different types of energy stores. Two, to understand that energy can be transferred from these energy stores to another energy store. And three, to recall and apply the different formulas for kinetic and gravitational potential energy. Okay, and then finally, the principle of conservation of energy to solve problems will also be covered. So let's start off with some possible scenarios involving energy. So you see over here three different scenarios where energy is involved, okay, whether they are being transferred from one store to another store, one object to another object. Okay, so energy is required for things to work, and the SI unit for energy is joule. So in this chapter, we are going to learn about six different energy stores. Okay, so there are three energy stores on the left. You will see over here the kinetic store, which is associated with movement, the elastic potential store, which is associated with objects which are being stretched or compressed, the internal store, which actually we covered in chapter 7, okay, which is the energy associated with the heat of an object, the gravitational potential store, which is associated with something being lifted off the surface of the earth, the chemical potential store, which is associated with the energy in the bonds of each of the chemicals, and the nuclear store, which is energy in the nuclei of atoms. Now, for the nuclear store, that is actually going to be covered as the last topic in Sec 4 under radioactivity. So, energy stores, okay, are based on the ideas of systems with different parts. So, actually, for the gravitational potential store of an object, it is the energy store between the object and the Earth as a system. Okay, so when we refer to the gravitational potential store of an object, we always actually include Earth as part of the system. Because if the Earth didn't exist, okay, the object is floating freely in space, it would not have a gravitational potential energy. So the next thing to think about is the transfer of energy. Okay, so energy is non-physical, it's an invisible substance. Okay, you can think of it that way, that's transferred from one store to another store. And the total amount of energy remains constant. So the analogy that I often use is you can think of energy as being money in your bank account. Okay, so for those of you who maybe you have a online banking app on your phone or you use online banking on a computer, if you have multiple accounts, you will realize that when you log in, you will see that maybe there's a list of different accounts. And in each of these accounts, there are separate amounts of savings. So the energy store is like different accounts, okay? And you are able to differentiate between perhaps your PayNow or PayLah, okay, and something else for longer term saving, perhaps an account where you are saving for your holidays or you are saving for a big purchase for your birthday or something along those lines. Okay, and of course, energy can be transferred from one store to another store, just like how cash, okay, money can be transferred from one account to another account. The four different pathways that energy can be transferred from one store to another store are mechanically. Okay, so by a force acting over distance. For example, when you push something or you lift something, you are exerting a force on it to cause it to move. So that is moving energy from one store, perhaps your chemical potential store, into the store of the object, in a way, transferring energy from one place to another place. Another pathway is heating. So when you have a temperature difference, you are transferring energy. Usually, the energy store involved is the internal store. Propagation of waves. Okay, there are electromagnetic waves and mechanical waves. We'll actually learn more about this in chapter 8, 9, and I believe 10. So I won't go into too much detail there. And also electrically, okay, so when you have electric forces, okay, charges moving through a potential difference. We will also learn about this, okay, when we get to the topics on electricity. So, some examples. Okay, energy transferred mechanically by a force acting over a distance. So, in this example over here, you see that you have a force being pushed. Sorry, a force acting on an object pushing it. And as the object is pushed, it travels over a certain distance. Okay, this increases the energy in its kinetic store. Assuming, of course, that there's negligible friction, so the surface is smooth. Okay, by Newton's second law of motion, the resultant force that applied to the object will cause it to accelerate, and this will increase the energy in the kinetic store. Of course, this doesn't tell you where the original energy came from, because the force over here, we actually haven't given you much details about it. Heating due to temperature difference, anytime you are cooking something, okay, that is energy being transferred by heating. You've got two objects at different temperatures, the pan and the butter, for example. And this is transferring energy store, the internal store of the pan to the internal store of the butter. By propagation of waves, okay, in this example, the girl is kicking a ball in a field on a sunny day and she feels warm, okay, because the electromagnetic waves from the sun actually are a way of transferring this energy from the sun to the girl. Again, in the form of to the internal store of the girl, where she starts to feel warm. Now, the other type of waves are mechanical waves. So, for example, sound wave, where the air particles are moving in a wave motion. Okay, we'll talk about that a little bit more when we get to that topic. But just need to know that sound is a mechanical wave, and you can actually transfer energy, okay, using sound. So there is that movement of the air particles in sound, and those movements actually are able to transfer energy to your ears to vibrate your eardrums, and that is how you are able to hear. Okay, so some other energy transfer, burning of charcoal, okay, over here. So when you are burning the charcoal, again, there is energy transfer by heating, okay, and also by some form of electromagnetic radiation, because it gives off some infrared radiation. And then electrically, in electric currents, okay, when you close the switch, the electrons, charged particles, travel across a potential difference. Okay, these are terms you might remember from lower secondary science, but if you don't, you're not familiar with them, don't worry, we will cover them in future chapters. But basically, anything to do with electric circuits and electricity, there is a energy transfer electrically. Okay, and over here we have energy transfer when nails are hammered into a wooden block. So this would be a mechanical transfer, because when the hammer hits the nail, it is exerting a force on the nail and the nail is moving. So that would be a mechanical transfer. Afterwards, okay, maybe the sound, that is transfer of energy through waves, a mechanical wave. So there are many different types of energy transfers that go on, and many different ways that the energy transfers can happen. Multiple stores, multiple transfers. So that is why we need to be very, very clear about the different stores, the different transfers, in order for us to describe what is happening very, very clearly. So to calculate the size of an energy store, okay, we've got two equations for this part of the chapter. This you actually might remember from lower secondary science. The kinetic store of a body is given by the formula Ek, which is in joules, the energy in the kinetic store, equals to half mv squared. Again, we always use SI units, so the mass must be in kilograms, and the speed or the velocity of the body must be in meters per second. Please be very careful that you are squaring the speed. Okay, this is a very common mistake. Some students might forget that and just put half mv. That would end up with the wrong answer. Next, for the gravitational potential store. Okay, EP, so the potential energy is equals to mgh, the mass times the gravitational field strength times the height. So G we actually have seen before in our previous chapter on mass, weight, and density. The number here usually is 10 because we are talking about on Earth's surface. However, if okay, it is on a separate type of celestial body, let's say on the moon, then the value of g would differ, and you would have to be very careful to refer to the question to find out what that value of g is. Okay, and as always, all our units must be in SI. So joules, kilograms, newtons per kilogram, and meters. Remember to convert, okay, if any of our units in the questions come in non-SI units. So let's move on to our worked examples. Okay, our first worked example, a golf ball has a mass of 0.05 kilograms. It's traveling at 5 meters per second, and we want to find out the amount of energy in the kinetic store. So very simply, we just apply our formula, Ek equals to half mv squared, substitute our values inside, and this will give us our answer of 0.625 joules. Pretty straightforward. Now, for worked example 2, same thing. Okay, we've got a box of mass 15 kilograms lifted 10 meters above the ground. So same thing, to find our gravitational potential store, we just use the formula EP equals to mgh. Substitute the values given by the question, 15 kilograms, 10 newtons per kilogram, 10 meters, and we're going to get 1,500 joules. Okay, so these two examples, nice and straightforward, because we are just simply substituting values into the correct formula. So you must remember the formulas, substitute the values, that would give you, okay, a very straightforward way of getting the answer. So just a quick summary, we've got energy required for things to work, which has the SI unit of the joule, and the 4 different ways it can be transferred from one store to another store, as well as our 2 formulas, half mv squared and mgh for kinetic and gravitational potential store respectively. If you want to review these things, you can go and pause the video, go back earlier and rewatch the video again. Okay, if not, let's move on to the next part of the lesson, the principle of conservation of energy. So the conservation of energy, okay, is a simple statement that tells us that energy cannot be created or destroyed. It can only be transferred from one store to another store or one object to another object. So in this example over here, okay, where you strike a match, what you're actually doing is transferring 20 joules in the chemical potential store of the match head, which has all the chemical bonds that's storing the energy, and you are transferring it via heating to the internal store of the surroundings, because the match head is going to get hot and is going to warm up, let's say for example, the air around it. However, this 20 joules does not disappear. Okay, the initial state is 20 joules in the chemical potential store, the final state is 20 joules in the internal store. It could be in different objects as well. It doesn't need to be 20 joules in the chemical potential store of the match going into 20 joules into the internal store of the match. As long as the total energy is 20 joules, then this is conserving energy. So like I said just now, energy cannot be created or destroyed. It can only be transferred from one store to another store, and the total energy of an isolated system is constant. So by isolated, what we mean is that in this system, no energy is entering, no energy is leaving, because it is not interacting with anything outside of it. So for example, okay, an example of an isolated system is, let's say, a ball that is left on the floor. It is, nobody is kicking it, okay, there's no wind, so therefore it's not interacting with the outside world. However, if we then consider, okay, for example, the sun is shining on the ball and therefore heating it up, okay, it is gaining energy through electromagnetic wave, then the ball itself would not be an isolated system, because the sun is actually constantly providing energy into the system of the ball. So we have to be very clear about how we draw our system, okay, and how we consider the energy flowing in or out of the system when we say it's isolated. So to illustrate the principle of conservation of energy, let's use an ideal pendulum, okay, that is swinging back and forth in the absence of air resistance. So when there's no air resistance, okay, that means that this pendulum is going to swing forever, because what we have is the energy being conserved within this system of the pendulum and the earth. So on the left side here, we have our pendulum at its highest point. So because it is at its highest point, that means it is not moving, it has stopped. And it has some energy in the gravitational potential store. Okay, I'm just going to represent it with a bar over here. And with the kinetic energy and the kinetic store, it's empty because the pendulum is at rest, okay, and at its highest point. Now, when it is swinging and it is now at its lowest point, okay, we can say that the gravitational potential store is minimal. We just put it at 0. So this one here is the lowest point. But because it is at its lowest point, it means that it must have swung and accelerated due to its weight. It is also therefore traveling at the highest speed. Okay, so we just say it's fastest at this point, and the same amount of energy, okay, as what was just now in the gravitational potential store is now in the kinetic store. And then finally, when it is swing over to the right hand side, again it is going to be at rest and also at its highest point. So again, it is going to be a repeat of what is happening on the first scenario, which means that, okay, this energy over here is all going to be in the gravitational potential store with nothing in the kinetic store because it is not moving. So you can see over here that the energy is conserved. Okay, it does not change in total. All it's doing is moving from one store to another store back and forth, from the gravitational potential store to the kinetic store and then back to the gravitational potential store. And then as the pendulum goes back, okay, returns back from the right hand side down to its lowest point, the whole process repeats. Gravitational potential store transfers to the kinetic store, and then as it swings back to the highest point on the left, again to its gravitational potential store. So now we've got a worked example. Okay, we've got a basketball of mass 600 grams dropped from a height of 7 meters, and we want to calculate the velocity just before it hits the ground. So over here, just before it hits the ground, very important, what this tells us is that at this point, the height is 0 meters. Okay, it is just before it hits the ground. It hasn't hit the ground yet, but right at the instant before it hits the ground, it's basically at 0 meters above the ground. So the height here is 0 meters. So first, we write our very important statement. By the principle of the conservation of energy, the initial energy of the basketball equals the final energy of the basketball. So initial energy, okay, it is dropped, meaning initially it has 0 joules of kinetic energy because it is at rest when it is released, it is dropped. As for its gravitational potential energy, we use the formula mgh. And you can see over here, I've converted 600 grams to 0.600 kilograms, okay, because the SI unit for mass is kilograms. And then going through the math, that gives us 42 joules. So our total energy is the sum of these two stores, 42 joules. Our final state is just before it hits the ground. So just before it hits the ground, the potential energy is 0 joules because, like I said earlier, the height is 0 meters. You could put mgh and then substitute h equals to 0, okay, but I've skipped that step, just as how I skipped the step of half mv squared v equals to 0 in the initial energy stage. So what that means is that our kinetic energy, half mv squared, must be equal to 42 joules because the total energy is 42, right? So all of it is in the kinetic energy. And if you substitute that, okay, we find that 42 joules equals to half times 0.600 kilograms times v squared. So if you do the math, you will find that v squared equals to 140. Put that into your calculator, take the square root, and you will get v equals to 11.8 meters per second. Of course, as per usual, we use three significant figures. Okay, the calculator answer I believe is 11.83 something. So we just round off to 3SF to give us our final answer. For our worked example 4, okay, what we have here are the LOL diagrams. These are very useful ways for us to look at or represent the energy being transferred into or out of a system, okay, in the initial state and the final state. So you see over here, we call it an LOL diagram because the graphs on the left and the right representing the initial and the final energy look like L's, and we have an O representing the system itself. So for worked example 4, okay, we've got a crane powered by a diesel engine lifting a stationary load from the ground floor to the 30th floor of a building. And we want to represent the crane and the load, okay, as the system. So first thing that we do, okay, we write down what our system is inside the O. So this is going to be crane plus the load. And then we ask ourselves, is the energy transferred into or out of the system? Okay, we can consider that a little bit later. But what is the initial energy of the system? So it says it has a diesel engine. So given that it has a diesel engine, diesel being a form of fuel, this means that it is going to have some sort of energy in the chemical potential store. Okay, I've represented it as 5 units here. You can use any number of units. The most important thing actually is the trend. Okay, so afterwards, E represents the elastic potential. Nothing here is being compressed or stretched, so that's 0. Gravitational potential store, because our stationary load is on the ground, let's put it at 0 as well. Internal store, okay, our diesel engine, we can say maybe it has a bit of temperature, quite hot because it is a diesel engine. Maybe it was already running or it's a hot day. We just put it at 1 unit. Kinetic store K, it says it is stationary, the load and the crane, so again 0. And the nuclear store also 0, okay, because over here we don't have any nuclear reactions going on. So this tells us that our initial energy of the system, what we have is 6 units. Is there energy transferred into the system? No. Okay, we're not going to transfer any energy into the system because this crane is going to lift it using the diesel fuel. So energy transferred out of the system. Maybe because the diesel engine is going to be very loud, it's going to be very hot, we can say that there's 1 unit, okay, being transferred out, okay, via heating because it is hot, and via mechanical waves or sound. Okay, so heating plus sound, maybe we say there's 1 unit. So what that means is the final energy must be 5 units left. And how can we represent our 5 units? Let's consider, okay, the chemical potential energy. Let's say that it has burnt off all the diesel. So now there is no chemical potential. Again, elastic potential also 0 because it is nothing is being compressed, nothing is being stretched. But now the load has been lifted, right? So it's lifted to the 30th floor. Definitely it has gained some gravitational potential energy. So our gravitational potential store, we could, let's say, put 3 units. Okay, why have I put 3 units? Because I'm also going to say that perhaps after running the engine, it's gotten hot. So it has some more energy in the internal store. It's gone from 1 unit to 2. But at the 30th floor of the building, it is still going to be stationary. So 0 kinetic store and no nuclear reactions have happened. 0 nuclear store. So you can see over here, okay, what I have is 5 units in total in the final energy of the system because 1 unit has been, okay, transferred out of the system here. So I'm going to repeat this, but not so detailed for worked examples 5 and 6 and 7. So over here we've got a truck moving at speed and we want to find out the energies involved. So it's moving at speed on level ground. So level ground means that it tells us our gravitational potential stores initially and finally, they are going to be the same. It uses its brake to come to rest. So kinetic store finally is going to be 0. Let's say initially it's moving very fast. Okay, let me clean that up. So the kinetic store initially, I'm going to put 5 units, for example. Okay, no nuclear store, no nuclear reactions. And because it's using its brakes, okay, it's not using any fuel. Chemical potential store also at 0, no change. And elastic potential also 0 because nothing is being stretched or compressed. Now the internal store, maybe I'll just leave it at 0 over here. So our initial energy is 5 units. Is energy being transferred into the system? No, I'm not going to say that energy is transferred into the system, but energy might be transferred out of the system because as the truck comes to a rest using its brakes, okay, the brakes might get hot, it might end up emitting a lot of heat, and it's also going to emit a lot of sound. So because of that, okay, let's say I transfer 3 units out and via heat and sound. Okay, and our final energy must therefore be 2 units. So therefore, I put here 2 units in my internal store at the end. So you can see over here, initial energy and final. Okay, even though they're not the same, the difference is accounted for by the energy transferred out of the system. Work example 6, we've got a metal pot. Okay, and there is soup at room temperature placed on the fire. So when it's first placed on a fire and when the soup is boiling. So there is no movement here. There is no nuclear as well. Okay, it is not being stretched or compressed, and we're not raising or lowering it. So I'm going to put 0 for all of these. And at the same time, are there any chemical changes in the soup when it's boiling? No. So also chemical potential is going to be at 0. Now, in it, the internal energy, maybe at first there is some, okay, it's at room temperature, so we just put 1 unit. It is being heated by an external source, so energy is being transferred into the system through heat. I'm going to put 4 units, but it's really up to you how you would want to, put the numbers as long as you have conservation and the trends, the logic is sound. Is there energy transfer out of the system? Perhaps as it is being heated, as it is getting closer and closer to boiling, it is also going to be losing energy out of the system to the surrounding air by heat. So maybe I can say that it loses 1 unit. Again, also by heating. So that means that our final energy is 4 units, and we can represent it using a bar here that has 4 units. So you'll realize what I'm actually doing here is using the LOL diagram to systematically consider, okay, our transfer of energy into and out of the system. This LOL diagram is not going to be tested, okay? It is really just a way to train yourself to think about the different energy stores and the different ways energy can be transferred into and out of a system. So that is going to be the end of the first part, okay? And in the next video, we are going to look at the second part of this chapter, which is about the work done and power.